Okay, well, it is a pleasure to introduce once again Professor Phillip Griffiths from the IAS. He is going to give this more detailed second part on the role of curvature in algebraic geometry. So, Professor Griffiths.
Thank you. The other day I talked some about the classical appearance of curvature in algebraic geometry, the Kadara vanishing theorem, and how it was used to characterize which compact complex manifolds are projective algebraic varieties, essentially to characterize when a line bundle is ample. It's when it has a metric whose Chern form is positive. There are extensions of that I mentioned where you take the usual metric in a line bundle and you multiply it by singular weight functions and use those rather than smooth metrics. And those give you a way of using, if you like, complex analysis to get at vanishing theorems for sheaves that are not bundles, ideal sheaves of points, things of that kind. I also mentioned another type of singularity called Poincare singularities, and just very briefly gave the definition of those. Those have arisen historically in what is called Neven-Lena theory back in the 70s and 80s, and more recently in some problems arising from trying to use Hodge theory to study moduli. So I'll talk a little bit about that. And then one topic that I didn't get to is hyperbolicity and the role of curvature in hyperbolicity. So what I'd like to do is talk a little bit about how Hodge theory, how curvature comes in through Hodge theory to study moduli of algebraic surfaces of general type. Moduli of K3 surfaces is a very classical subject, a lot of works, very beautiful subject. And Hodge theory is used for K3 surfaces because of the global Torelli theorem, that the Hodge structure on cohomology uniquely determines the surface. And then, so that gives you, so to speak, a picture of the moduli of K3s over the smooth part, or more generally over the part where the K3 surface has what are called canonical singularities. Those are singularities that don't affect the Hodge structure. Particular interest is, or special interest, is what happens at the boundary. How do you complete or compactify the moduli space? And there are two classical compactifications. One is called Satake-Baily-Borel, and the other is toroidal. And what I want to do today is to talk a little bit about the Satake-Baily-Borel and the role of curvature that's used to define the Satake-Baily-Borel for moduli of surfaces of general type beyond K3 surfaces. So just a little bit about moduli. As I mentioned the other day, Kolar, Shepard, Barron, and Alexiev have defined a moduli space for surfaces of general type that have given numerical characters. Usually one takes the irregularity, that's the first Betti number, to be 0, regular ones. Then the PG, that's the dimension of the space of holomorphic two forms, or the global sections of the canonical bundle. That's called PG, or H20, the Hodge number. You fix that. And then you look at kx squared, the degree of the canonical bundle. Since it's of general type, that's positive. K3s, there the canonical bundle is trivial. The PG is 1, and the space of all polarized Hodge structures that have H2, 0, 1. So the possible Hodge structures for K3 surfaces, that's what's called a bounded symmetric domain. Those are very special homogeneous complex manifolds. Satake-Baily-Borel used the very extensive theory of bounded symmetric domains to compactify the quotients by discrete groups. And that's what you stick onto the boundary to pick up the Hodge theory, or some of the Hodge theory, when the K3 surface becomes singular. We're particularly interested in the non-classical case. And for simplicity, take the case where the PG, the Hodge number H20 is 2. That's the first case that you come to. And where the kx squared is either 1 or 2. That's the smallest degree that you can have for the canonical bundle. Okay. These are very beautiful surfaces. The first one was very well known classically. The second one was studied extensively in the 70s by Horikawa. For both of those types of surfaces, what is called the local Torelli theorem holds. That means the Hodge structure of that surface, at least locally in moduli, determines the surface. So to use Hodge theory to try to study moduli is was a plausible strategy. Just to say a couple of words about the compactification, the canonical compactification of Polar, Shepard, Baron, Alexiev. What that means is that if you have a family of smooth surfaces of general type over, say, a punctured disk, then there's a canonical way of putting in a surface over the origin. It's like for curves, you can uniquely put in a stable curve over the origin. For surfaces, you can uniquely put in a surface with certain singularities called semi-log canonical. Just to tell you briefly what those are, if you resolve the singularities, the semi-log canonical singularities have first a double curve. That's at a general point, it just looks like two planes intersecting transversely, and at a finite number of points, those two planes come together. They're called pinch points. So it has a double curve with pinch points. And then it'll have a certain number of isolated singularities. And those are described in the literature in the following way. So here, let's just take S to be a normal surface. Get rid of the double curve, it makes it simpler. You take a resolution of singularities, and then over Q, I'll explain what that means. You pull back the canonical bundle of the normal surface. It's related to the canonical bundle of the smooth surface by some divisor with normal crossings with rational numbers as coefficients. The way rational numbers get in is that if you have a surface with an isolated singularity, the definition of the canonical bundle is that you look at differentials, regular differentials defined outside the singularity. That gives you a sheaf over the surface, and that's the canonical sheaf. It's so-called divisorial sheaf. This sheaf need not be a line bundle. Okay. The sheaf need not be a line bundle. In other words, the canonical divisorial sheaf may not be a line bundle. You always assume that some multiple of it is. It's some so-called Q Cartier. So the thing itself may not be a line bundle. You could imagine if you take a quotient singularity by a finite group, something will happen that you have to multiply by, say, the degree of the group that you divide by to get a line bundle. That's the sort of thing that happens. So you get this formula here, and the definition of semi-log canonical is these coefficients should all be bigger than or equal to -1. I wondered what that meant when I saw it. And there's a very simple way to understand it analytically. If you assume that the thing is a line bundle, then a section of this is a differential downstairs on the singular surface defined outside the singular point. Pull it upstairs to the smooth surface. It's going to have poles on this divisor with normal crossings that you get by resolving the singularity. Those poles should be at most first order, logarithmic. That's what it means. If you have to go to a power of the line bundle, you have the same phenomenon. You pull something back and it should have at most a first order pole. That's where that -1 comes from. So for example, if the singularity is gotten by just taking an algebraic curve with nodes, smooth curve maybe with some double point, and taking a cone over, that's an isolated singular point on a surface. And the condition is that the arithmetic genus of that curve be less or equal to 1. So if you just have a smooth curve, you're not going to get a log canonical singularity unless you're taking a cone over a smooth elliptic curve. Genus 2 doesn't work. Coming back to moduli, there's no example where the structure of the boundary of moduli has been worked out. I think people know locally what the surfaces look like, but there's not a global picture. It's a very interesting recent work by Frangini, Pardini, and Walensky that do the case, the first case, where the kx squared is 1. They do some of this. It's the only thing I'm aware of in the literature. So one natural thing that's suggested is to use Hodge theory. If we can't directly get at the boundary algebro-geometrically, let's at least map the surfaces on the boundary to their limiting Hodge structure and see what that looks like. And from that, try to deduce information on what the surfaces can be. Historically, this was the way that the moduli of curves, David Mumford and others, but especially David did. He got, I think, the first picture of what the boundary of moduli of curves should look like by knowing how the Hodge structure degenerated. So the classical case is when the PG is 1, you have a bounded symmetric domain. That's curves and Boolean varieties for weight 1, K3s, for surface weight 2. And these are the ones that we were interested in, that I just described. Just to tell you what these period domains are, just to remind you, if you take the set of polarized Hodge structures of given weight, so we think of the nth cohomology on a smooth algebraic variety, that's weight n. And look at all possible Hodge decompositions with given Hodge numbers, and they satisfy the Hodge-Riemann bilinear relations. That's a period domain. It's the set of all potential Hodge structures that could come from an algebraic variety of somewhere. And these things are homogeneous complex manifolds. The simplest one is the classical upper half plane. For algebraic curves, you have the Siegel generalized upper half plane in your genus G. For K3 surfaces, I'll say what it is in just a minute. So classical weight 1 algebraic curves is the Siegel upper half plane, symplectic group divided by the unitary group. For weight 2, the domain is a special orthogonal group 2a comma b divided by the unitary group, and A tends to special orthogonal in B, where A is the Hodge number H20, B is the Hodge number H11. This is Hermitian symmetric only when this number is 1. That's the K3 case. So we're interested in the first non-classical case. So what happens to the Hodge structure when a family of surfaces degenerates? This is an extensively studied subject back in the 1980s by Catani, Kaplan, and Schmidt, also Kashiwara and others. So it's well understood how Hodge structures may degenerate. We'd like to use that to know how can the algebraic surface degenerate. So the Hodge theoretic space has certain boundary components, and presumably there are then boundary components in moduli that lie over these, and the stratification should line up and so on. So you want to, if you like, get a guide to what happens algebro-geometrically from the Hodge theory. So your singular surface, one of two things can happen when the surface degenerates. Either the Hodge structure can go to infinity, go to the boundary, or it can remain in the interior of the period domain. Algebro-geometrically, what happens is that the only singularities that send you to the boundary are the Gorenstein ones. So already you see the sort of algebraic geometry and algebraic geometry interacting. Gorenstein means that the canonical sheaf should be a line bundle. You don't have to take a multiple. If you have a non-Gorenstein singularity, those have finite monodromies. When you turn the surface around the origin, you just follow it around the origin and see what happens in homology. You get a finite group. Those are the non-Gorenstein groups. So what about the image of the compactified moduli space sitting in some kind of extension of the moduli space for Hodge structures? Here the curvature enters in the following way. You have the extended Hodge bundle, and like I said the other day, the determinant should not be here. It should just be that you have this family of surfaces lying over moduli. You take the relative dualizing sheaf. That's a line bundle. And the result, which is basically proved, is that the image of the compactified moduli space, that this line bundle is ample on this image. So the image of the, and this is going to be the analog of the Borel-Baily-Satake compactification. So algebro-geometrically, it's proj of the extended Hodge line bundle. So I'm not going to get into how this argument goes. Just back up. The essential point in the argument is where? Yeah, the essential point is that the extended Hodge bundle, this direct image of the relative dualizing sheaf, okay, is positive in the differential geometric sense, provided you allow the metric to have these Poincare singularities. Okay. So what you need really for this theorem is the old Kadara theorem, but extended to the case where you have metrics which may not be smooth, but they have only these Poincare type singularities. So it's another way in which curvature is coming into algebraic geometry, in this case through Hodge theory as applied to moduli. I think I'll skip over this, which is just talking a little bit about some of the Hodge theory behind, some of the analysis behind that, and go on to curvature and hyperbolicity. And we'll just close with that. So this is a different topic. You have a complex manifold that has a Parisian metric in the tangent bundle. Then there's a canonical connection that I mentioned. The good ones for complex differential geometry by and large are the ones that are Kähler. Kähler means there are many equivalent definitions, but one of the ones that's most useful in practice is the following: that you have this complex manifold, you have a metric which is ds squared, which is the sum of hij j bar, dzi, dz j bar. And you ask, how simple can you make that metric by changing coordinates? Well, it's easy to make the coefficient matrix the unit matrix at the origin. That's just algebra. The Kähler condition is you can get rid of the first order term, so that the ds squared oscillates to the Euclidean ds squared to second order. That's equivalent to Kähler. So that means that any identity that involves only first derivatives that holds in Euclidean space holds on a Kähler manifold. That's the basis for all these Kähler identities. So you have the full curvature tensor. It has Hermitian matrix as coefficients and two forms, or differential forms of type 1 as entries. The holomorphic bisectional curvature is something that you get when you take a pair of complex vectors in the tangent space. Complex vector will span a real, it and its conjugate, a real two-dimensional plane, and take two of those. Then there's what's called the holomorphic bisectional curvature. That's this thing here, ij bar, ij bar. Then there's the holomorphic sectional curvature. That's like the Riemannian sectional curvature, except it's in a complex plane in the tangent space. And there's the Ricci curvature, which is the trace of this Hermitian matrix, and the scalar curvature, which is the trace of the Ricci. The Ricci is a differential form of type 1, which is Hermitian, it's real, so it has a trace. The Ricci is what turns up, for example, as the first Chern class of the minus the first Chern class of the canonical bundle. Unlike in the Riemannian case, where the sectional curvature is the average of the Ricci, the Ricci curvature is the average of the sectional curvatures. This is no longer the case in the complex case. The connection between the two most useful ones in algebraic geometry are the sectional curvature and the Ricci curvature, and they're not related, unlike the Riemannian case. The one relation that is known is that if you have negative holomorphic sectional curvature, then you have negative scalar curvature. It's an old result of Piaget. Ricci curvature being negative. Remember, that's a 1 form. It's the first Chern class. It's a differential form representing the first Chern class of the negative of the canonical bundle. So if it's negative, the canonical bundle is positive, then you have general type. And these are there's then a canonical metric that makes it a so-called Kähler-Einstein manifold. This is the Yau theorem, the Alban-Yau theorem. Holomorphic sectional curvatures comes in by virtue of the Alfor's lemma. The Alfor's lemma is this amazing tool in complex geometry. For one complex variable, if you remember your complex function theory, if you have a holomorphic function on the disk, it maps the disk to the disk. So f of z is, the f takes the disk to the disk, and f of z is a norm less than 1 for z less than 1. And if the origin goes to the origin, the Schwartz lemma says that f at any z is less than or equal to z. So you can, f takes z no further from the origin than z. Another way of phrasing that is if you look in the Poincare metric in the disk, that any holomorphic map of the disk to the disk decreases distance in the Poincare metric. Poincare metric is invariant under the automorphism group of the disk. I just gave you this distance decreasing statement for geodesics going out from the origin, and now apply the automorphisms and you get it for anything. So the Schwartz lemma says that any holomorphic map of the disk or the upper half plane to itself decreases distance in the non-Euclidean geometry. All fours said that really what you want is that you're mapping the disk into a complex manifold. This is what's going to be interesting for algebraic geometry. And if that complex manifold has negative holomorphic sectional curvature, then you have the distance decreasing property. That's the all fours lemma. So it's the Schwartz lemma, but where negative curvature is assumed on the target space. So for example, if you know that if you can write down on the Riemann sphere minus 3 points a metric with negative curvature, suppose you don't know that the universal covering is the upper half plane of the disk. Suppose you can just write down a metric with negative curvature on the Riemann sphere minus 3 points. It's pretty easy to do that. You just write the formulas down and you make it look like the Poincare metric around each of the punctures. You make some choices and you get a metric of negative curvature on P1 minus 3 points. Then the distance decreasing property says that any holomorphic map of a disk into the Riemann sphere minus 3 points, there's a bound on how big the radius can be. You just take this distance decreasing property and see what it tells you. That's the Picard theorem. The generalization of the Picard theorem, you'd like to say, well, we'll use similar argument that the universal covering of P1 minus 3 points is the upper half plane. We must be able to do something like that in higher dimension. And since the uniformization theorem doesn't hold, you need to have something that's some different tool to be able to use to study holomorphic maps into algebraic varieties in higher dimensions. And it's the curvature that plays that role. So there are two long-standing conjectures. One is that if you have a general type, well, I should say that a complex manifold is said to be hyperbolic if there's no non-constant map of the complex line into it. So you can't map C into it. So for example, a K3 surface is not hyperbolic because it has on it elliptic curves, and the universal cover of elliptic curve mapping to the curve goes into the K3. But as soon as you get into higher Kadara number non-zero, then you begin to get hyperbolicity. And once the Kadara number is 2, then the conjecture is that it becomes hyperbolic modulo a proper subvariety, meaning that any holomorphic map of C into this surface of general type has to lie in a given set of algebraic curves. So there are only finitely many possibilities for where it can go. Or the general conjecture is that a general type algebraic variety is hyperbolic modulo a proper subvariety. I'll say what is known about this in just a moment. Second long-standing conjecture is that if you have negative holomorphic sectional curvature, then X is of general type. So this would be a relation at the level of algebraic geometry between the holomorphic sectional curvature and the Ricci. If it holds, it has to hold for subtle reasons because there's no relation between the Ricci tensor and the holomorphic sectional curvature. Regarding the first one, it's known that if you have general type or a positive canonical bundle, the first thing that you would like to do is to use that positivity to construct sections somewhere that would give you a tool to work with. And the sections that people try to construct are what are called symmetric differentials. Those are sections of symmetric powers of the cotangent bundle. So what you're trying to say is that if the determinant of the cotangent bundle is positive, then there should be enough positivity in the cotangent bundle itself to get sections at least of some high power of it. That's false. Doesn't work. What one knows is that you have to go to higher order geometry to get at this using jets. So you look not just at the first derivative of the map in, but you take the jet, which is first, second, and third up to some order k. Look at those derivatives. It's, if you like, geometrically what you're doing is you're looking at a curve in a surface, and you've got to thicken the curve a little bit by putting in higher order information to make it more like it has dimension 2. That's the sort of intuition behind this. So what's known is that general type implies that the Euler characteristic of the sheaf of jet differentials is growing like a positive line bundle. It was proved a few years ago, it's a very beautiful argument by Desmaillet, that from the Euler characteristic, which is the alternating sum of the dimensions of cohomology of powers of some bundle, that you can dig out the H0 if you have certain positivity, which these jet bundles do. So Desmaillet proved that the global sections of this jet bundle look like the sections of a big line bundle. So in fact, this bundle of jets is big, and it's Neff. So you're well on your way, but it has a horrible base locus. That's been the problem. The only case it's been dealt with is the case of surfaces where C1 squared is bigger than C2 as a result of McQuillan, who proved this conjecture in that case. There are other special cases that are known, like taking very high degree hypersurfaces in projective space and so on. They use jets in one way or another, but the only sort of clear result that I know of is this one. Regarding B, this is a statement that negative holomorphic sectional curvature implies general type. It's been known for some time that this would follow from one, and I think probably the main outstanding conjecture from the minimal model program, so-called abundance conjecture. The abundance conjecture says if the canonical bundle is big and Neff, then it's free. So multiples without base points. That's not known. Just this year, a few months ago, Wu and Yao proved B using a Monge pair equation argument. It's a very beautiful argument. So this second conjecture B is known, and so far the proof is not uses analysis. It's not an algebro-geometric proof. It has an application to moduli and Hodge theory. If you take any sub-variety of one of these period domains quotient by an arithmetic group, then which is horizontal, I'll explain what that is in a minute, then this sub-variety is of general type, it's smooth. Horizontal means that the tangent bundle of X lies in a sub-bundle of the tangent bundle of this period domain that's given by what's called infinitesimal periodicity. When you have a family of varieties and you look how their Hodge structures vary, they have differential constraints. If those are satisfied, then you begin to get good curvature properties. And in particular, you get this negative holomorphic sectional curvature for any smooth X. And you have to use the curvature decrease on submanifold property that I mentioned, so that comes in. Suppose you had a moduli space now that is smooth, it's complete, and where local Torelli holds. Then that moduli space is of general type. That follows just from the Yao theorem applied to these submanifolds of these d-bicounts. Those assumptions that the moduli space is smooth, that's maybe not too bad. That it's complete, there are some of these, but that's not in general what you get. Usually in moduli spaces you get singular varieties occurring. And that that local Torelli holds, I think that's a reasonable assumption, because one can get around that by very descriptive. So the real thing you do want to assume is that it's compact, that it's complete. The conjecture of Vivek is, in general, for a moduli space of varieties of general type, it's what it is, that it's logarithmically of general type. General type means you have a lot of sections of powers of the canonical bundle. Logarithmic general type means you have a divisor, and you have a lot of differentials with only log poles on the divisor, or powers of that. So logarithmic general type is like general type, but allowing log poles on the divisor. Vivek's conjecture is that for the moduli space for varieties in general, a general type is log general type. I left off, well, that's what this means. So if you wanted to prove this, the first step would be to go back and prove the Wu-Yao theorem for singular varieties. Second step could be to prove it in the logarithmic case. What the Wu-Yao theorem is for smooth algebraic variety. You could also formulate a similar type of question for the logarithmic case. That means you allow the logarithmic singularities on a divisor. And then you have to allow singularities, because the image of these period maps, you take moduli and map to the space of Hodge structures, usually those images are singular, especially at the boundary. So if one were able to go back and do the analysis where now you have singular metrics, and do the analysis that Wu and Yao did, where you have singular varieties and singular metrics, then this Vivek conjecture would come out. The analysis in the Wu-Yao theorem is a Molge-Ampere equation. So it's like the determinant, it's the Laplacian of U is e to the u. It's that type of equation, highly nonlinear. And there's been nothing that I'm aware of from either the complex side or the algebro-geometric side that deals with that equation, where you begin to get the singularities of the sort that one is going to encounter in algebraic geometry. So when we're able to do this, it would be, again, a very nice way that curvature comes into very interesting questions in algebraic geometry, but that's, I think, a long way off. Thank you.
Any questions? So, with respect to this last point, you don't have an idea of how to incorporate these singular functions in the Molge-Ampere equation to at least write heuristically what equations one would have to deal with?
Do I have an idea? No. Are there ideas in the literature? The only ones I'm aware of are there's a group of people working in materials science, materials, the use of PDEs to study materials where you get singularities. Caffarelli and Nuremberg, and there's a whole group of people who are studying, in effect, Molge-Ampere equations with some kinds of singularities. The singularities, I think, have more to do with, since it's coming from materials, things that are like that, as opposed to smooth. Whether you allow, say, poles and things of this sort, I don't know. But,
And
I mean, you could ask the simple question, let's suppose you take a solution of the Moll-Ampere equation, and Laplace of u is e to the u. Take a sequence un, where un goes to a delta function. What happens to the Moll-Ampere equation?
And where you mentioned the work of Wu and Zhao, could you tell a little bit more of how this Moll-Ampere equation analysis implies the abundance conjecture?
No, it doesn't imply the abundance conjecture. The conjecture that negative holomorphic sectional curvature implies general type follows from the abundance conjecture. But
it's just that part.
So that there's an implication. Abundance conjecture implies this other one.
Okay. Now
we don't have the abundance conjecture, but we had Yu and Yao to prove this by PDE methods.
Perfect. Now I understand.
Yeah, that's an interesting question. Since you're proving something that non-trivially follows from the abundance conjecture, and you have a way of proving it over here, does it say anything about abundance conjecture? Not directly, but it's an interesting question.
Maybe even for a few cases or something.
Yeah.
Any other questions?
Yeah, is this Ricci curvature that you are using related to a notion of volume, as it is in the Riemann? Is this notion of Ricci curvature related to a notion of volume, as it is in the Riemannian case?
If you take the 1-1 form and take its highest exterior power, so you wedge it, so you get a top degree form, then you get the volume form. So it is related to the volume. And in fact, the Wu-Yao theorem goes through that relation. Since the relation to the volume form is that you take this 1-1 form and raise it to the nth power to get a determinant, it's not surprising that that the Moll-Ampere comes in.
Any other questions? Well, thank you very much.
Okay.